We're beginning our second day of the study of waves. Yesterday we learned about the two forms of waves. We learned the transverse wave and the longitudinal wave and how the particles will vibrate either up and down or left and right depending on the energy of the wave, perpendicular or parallel to the energy. Today we are going to learn a little bit about the anatomy of these waves. So we've had both the transverse and the longitudinal that we'll be addressing today. You see here the transverse wave has some new vocabulary for us. We have this position right here is called the crest. That would be the top of the wave. And down here we have the lowest part of the wave. That's called the trough, right? We're going to be mindful of this line here. This line represents what this medium would be doing if there was no energy moving through it. So if we don't have any energy, we're going to be at rest, we're going to be still, we're going to be calm, there won't be any ripples or vibrations. So there won't be any crests or troughs. So the displacement from that rest is measured by a quantity we call amplitude. Amplitude is the amount of disturbance there is. And we'll learn a little bit more about amplitude later. But amplitude is simply the difference between the rest position and the highest energy position, like the crest or the trough. So you could measure the amplitude as being from here to that position or from here to that position. Either way works. What you don't want to do is measure from the trough all the way up to the crest. That would be doubling the amplitude. You do not want to do that. Amplitude is going to be measured in meters. It's a distance, it's a displacement. So that is amplitude. Wavelength is another quantity that we need to know and be able to measure. It is a length of a wave, so it is measured in meters, just like every other length would be in physics. And this is the length that would incorporate an entire wave. So what do I mean by that? Let's see here. We're looking for positions on successive pulses that are identical. So we would measure from here to here, like the crest to the crest, for instance. And the length of this, if you have a measuring stick, we could figure out the length of this wave or the wavelength. Wavelength is measured in meters, like I said before, and we use a Greek letter lambda, as we see here in the bottom of the screen, lambda. It looks like a number 2 in a sense. It's a funky letter, but it's the way we're going to indicate wavelength. If you look at your reference table, you'll see lambdas in the wave section of formulas. Now, it says here that it's separated by 360 degrees. We'll learn about what that means in a minute. I'll go through that, how we can measure waves with degrees. But it's important for us to understand that you don't just have to measure wavelength from a peak to a peak or crest to a crest. You could also measure from a trough to the next identical position, which would be the trough of the next wave, right? So you can measure from there to there. You can measure from this position here to the next successive position, which would be there, the mirror position on the next wave, right? A good definition might be for wavelength that it needs to incorporate an entire crest and an entire trough. So here's an entire crest, and here's an entire trough. Again, over here, this is half a crest from this position to here. We have an entire trough, but then we have another half a crest here. So 2 half crests and 1 trough makes an entire crest and an entire trough. Let's look at longitudinal wave anatomy. Longitudinal waves, remember the particles are moving parallel to the disturbance, the energy motion. So the particles are going to be moving left and right, left and right, left and right, left and right, left and right. And as that happens, when they get bunched together, we call that area a compression. And the area between them is going to be called a rarefaction. So we have 1, 2, 3, 4 areas in this wave that are called compressions. And the distance between compressions, or the center of compressions, or identical parts of the compressions, would be called the wavelength. So we have wavelength in both longitudinal and transverse waves. Again, wavelength is measured in meters. Now, when we want to consider various points on successive waves, if you have 2 points that are doing the same thing as a wave moves through them at the same time, we say that they are in phase. So they're doing the same thing, they're the same displacement, they're moving in the same direction at the same moment. We say those 2 points are in phase. So if you imagine uh, a wave, like let's say the wave velocity is from the right of the screen to the left of the screen. It's moving from here to here. So A, as the wave moves this way, let's say this is like an item like floating on the sea, it's going to float upward as this crest moves from right to left under it. It's going to go up, then it'll go back down. Well, there's another position that's doing the same thing on its pulse, and that would be this guy over here, E. E is going to go up and down as well. So we say that these two, A and E, are in phase. They're going to be doing the same thing the next moment as each other. Um, Basically, we say they have a whole wavelength between them if they're going to be in phase. So we're going to practice this in a second, but A and E are in phase. B and F are in phase. C and G are in phase. D and H are in phase. So we call this in phase. Now, what I'd like you to do is I'd like you to practice this process. I'll tell you there's 2 questions on this board right now, and we have a wave that has several points indicated. Which pairs of points are in phase? So I'll tell you there's 3 pairs of points that are in phase. And why don't we pause the video? Now, the 2 points that are in phase are A and F. They are in phase. We also have C and H in phase, and we also have B and G in phase. They're doing the same thing on successive waves. Now, the next question is, which pairs are what we call 180 degrees out of phase? So I have not taught you about degrees and how they're related to waves yet, but this image shows that we have um, markings here on our x-axis that indicate degrees, right? So we see that basically a half a wave or an entire crest is 180 degrees, and an entire wave is 360 degrees. So a quarter wave is 90, then another 90, then another 90, and then a whole wave. So what we're looking for is pairs of points that are 180 degrees out of phase. Those points are going to be doing the opposite thing as each other. Like for instance, if this red wave is moving to the left, A is going to be moving upward as this crest moves under it. But while that's happening, something that's 180 degrees away, as the wave moves to the left, will be moving downward into the trough. They're doing the opposite thing as each other. I'll tell you, there are 4 pairs of points on this diagram, 4 pairs of points that are 180 degrees out of phase. Can you please find them? Pause the video. Okay, the 4 pairs of points we have are A and D. Those are 180 degrees out of phase. Then D and F are 180 degrees out of phase. And then C and E are going to be 180 degrees out of phase. If we move to the left here, the wave moves, you're going to see C falling down into this trough while E goes up the trough at the same time. And then we have E and H. They're also 180 degrees out of phase. So there are our 4 points that are 180 degrees out of phase. Now, where does this degree business come from? How do we relate degrees to waves? Now, in a math class along the way, maybe a geometry or a trigonometry class, you may have learned a little bit about something called a sine function or a cosine function, and we certainly covered it when we deal with angles relative to a horizontal or a vertical. So I want you to focus on the circle here. When this dot, that green dot that's going around the circle, is here, it's at 0 degrees. When it's here, it's at 90 degrees. So let's just focus on these 2 moments here. When it's here, it's 0 degrees. When it's here, it's 90 degrees. What a sine wave does, a sine wave marks the vertical position of this dot. So right now, the dot is descending, and now it's rising. It's at its highest point, back at the equilibrium, lowest point, and now back at equilibrium. So when you're plotting the vertical displacement of a dot as it goes around a circle, you're plotting the sine curve. If you're plotting the horizontal displacement of a dot as it goes around a circle, you're plotting the cosine curve. So the waves that we're seeing, that we're dealing with in this class, are going to be mostly sine curves, if not all. And you really don't need to know where this comes from. I just wanted to help you associate degrees with the circle, what's going on with a wave. So here's 0 degrees, 90 degrees, 180, 270, back to 0. So a whole circle is 360 degrees, and therefore a whole wave is 360 degrees. As a side note, we used to have a technology called Flash, Java, where we would be able to pause these little doodads to help us make some better sense of it and move it sequentially in a logical manner. But those are insecure and we can't use them anymore. They don't work on computers, so we just have to run these sort of programs that just keep going, and you can't really control them. You just got to catch up with it. Let's turn the page. The motion a particle on a wave will behave is like something floating on the surface of a water. So again, I can't pause this, but let's say we have a red cork floating on the water and a wave comes. Your job is to be able to predict as a wave approaches what that little red dot would do as a wave approaches it, right? That particle. It's going to go up, down, up, down, up, down, up, down, up. Now remember, these particles in transverse waves are not moving left and right. They're going up and down only. We learned that yesterday. As the energy moves from left to right. So it is perpendicular motion to the energy of the wave. Now, there's going to be several questions for you to practice on. Here's one right here, an example of one. Position A is a position in a medium, and this wave, this energy is going to move from left to right across the screen. It's going to move through this dot. So our job is to identify the next motions that this particle would move, right? So if this wave moves through particle A, you would see particle A go down into the trough as it approaches. Then it would quickly rise up and over the hump at the peak or crest, and then back down to the equilibrium line. So if, like in a multiple choice or a short answer, you would have to say the motion would be down, comma, up, comma, down. That's what it would be doing. And there, if it's multiple choice, there'd be all kinds of other options for you to select from. Amplitude of a wave is a measure of the energy of the wave. So the greater energy, the greater the amplitude, the greater the disturbance from that equilibrium line, the higher a transverse wave is, or the more compressed these compressions are in a longitudinal wave. So an amplitude sound wave is a longitudinal wave, and somebody screaming would be compressing a lot of these particles together very quickly and very efficiently. They'd be packed together, and they would move across the sound medium, whether that be air or water or a material like metal or solid. Light waves are manifested as bright when they have high amplitude. They're very bright. So we would see that light waves are transverse waves. So they would go, they would have crests that are very high and troughs that are very deep. So amplitude is measured by the energy. Now, here's an interesting phenomenon. Amplitude in this energy has no effect on the speed of a wave, right? If I was going to whisper to you in a classroom, you would hear my message no quicker or briefer than, or even longer than if I screamed at you. If I screamed at you, you would hear my message just the same amount of time. Um, so amplitude has nothing to do with the speed of the wave. So waves of less energy and more energy will have the same velocity. Okay? Waves of less energy and great energy will have the same velocity, even if they have different amplitudes. That's what that means. In order to change the speed of a wave, you need to change the medium that it's moving through. So it says here, a loud sound travels no faster than a quiet sound, although the loud sound will travel farther. Um, so um, I think I wanted mainly to say here that in order to change the speed of the wave, you need to change the medium. The medium is basically the speed limit of the wave. Um, we'll see later that sound moves faster through solids. It's carried much faster through solids than it is through liquids, and then it's even slower through gases, for instance. Because if you think about the way particles behave, solids have particles that are going to collide together much more efficiently and quickly because they're packed together closely. And then gases would be the opposite end of the spectrum. So thank you for listening. I wish I had a demonstration of that with me right now. But you need to change the medium to change the speed of a wave. Amplitude is not speed, it is energy. This is the last thing of the day, and then we'll do a worksheet. Which distance represents the wavelength? All right, so it's not up and down, it's the length of a wave, and it's not c. C is going to be half a wavelength, right? This is going to be just the length of a trough. A wavelength is from this base of this trough to this base of this trough too. That would be D. How many complete waves are shown in the sample? We just trace it. 1, 2. There's 2 waves here in the sample. And I want to ask a secondary question to this. If this, let's just say we were told that the length from this position to this position is 4 meters long. Let's say it's 4 meters from here to here. Would we be able to determine how long one wave is? If it's 4 meters from here to here, and we have 2 waves in that chunk of material, I would bet that each wave is 2 meters long. And we could write that on the board, like 4 divided by 2 meters gives me a 2. Which distance represents amplitude? It is not A. Many students will get this one wrong because amplitude is not from the trough to the crest. It is rather from the trough to the midline, which would be B as in boy. That concludes our study of the anatomy of waves. Tomorrow we'll have something new for you. Thank you very much.